All right, let us get started. So today will be our last full day of lecture. We're going to finish up discussing polarization, which we started last time. And then Tuesday, next week, will be the final exam review. So we're pretty much done, which may or may not be an exciting prospect to some of you. So let us go ahead and finish our topics. Polarization, that's what we started or ended the last class with. Polarization, if you remember, was a characteristic of light, where if you remember what light, of course, is electromagnetic wave, which means there is an electric field. So let's say this black wave here is the electric field. And then there's also a magnetic field which oscillates along with the electric field. And they oscillate perpendicular to each other. So that's kind of a representation. The electric field oscillating up and down, the magnetic field, this green one, oscillating back and forth, they're perpendicular, and the whole system propagates, let's say, from left to right here. That was light. That's what light is. Polarization is defined as the direction of the electric field. Okay, so obviously, the fact that the electric and the magnetic field are always there and they're always perpendicular to each other, it didn't matter when this was first defined whether we chose to call it the direction of the electric field or the direction of the magnetic field. They're equivalent. But someone made a decision, and that decision was, let's say it's whatever direction the electric field is oscillating, that's what we're going to call the polarization. And so if this is an example of the light, then we would say this light is polarized upwards, or technically up and down, vertical. But just to save a little time, we call it upwards polarized. And of course, the electric field were instead oscillating, let's say, left and right, and the thing was propagating upwards or something like that, then we'd say the light is polarized horizontally instead of vertically. And that light can be polarized in any direction. It could be a 30-degree angle, any which way. So that's fine. That's just defining polarization. All light is polarized because all light has an electric field. There is the term unpolarized light, which is important, but it's also a misnomer because unpolarized light doesn't really exist. I mean, all light has this electric field oscillation, and thus all light must be polarized. However, the term unpolarized light is actually referring to when a source of light, something which is emitting light, doesn't emit light whose polarization is in the same direction all the time. Rather, like the sun, the light that comes from the sun is just randomly polarized. Sometimes the light comes out of the sun where it's polarized upwards. Sometimes it's polarized at 48 degrees. Sometimes it's polarized horizontally. It's completely random which direction the polarization would be for the light coming from the sun. And so we call that unpolarized light. But really, it's randomly polarized. Now, what we saw last time was for our purposes, what we're going to do is we're going to try to figure out if we can create a material, which we do, which has the ability to filter the light based on its polarization, meaning this material has the ability to block light if the polarization is in the wrong direction, and let light through if the polarization is in the correct direction. We would like to figure out, can we predict how much light will make it through a system of polarizers, this material, if we set it up in a certain way? So one way to think about it is, if you have light whose polarization is up and down like this, and you have some piece of film, some material, and you put a bunch of vertical slits in this material, then when the light hits this material, because the oscillation, the waviness is up and down, vertical, and the holes in the material are also up and down, you get 100% of the light comes through. So this allows the light to pass through the material. However, if instead what you have is the light is polarized back and forth like this, okay, so kind of in and out of the page, it's hard to see it visually, but imagine the light waviness being in and out of the page as it propagates towards this material. Well, now it can't fit through these vertical slits because it's too wide. The waves can't fit through these vertical holes. And so for that, you'd have 0% of the light goes through. And so what we've created here is a material which can filter light. We can let some light through or block some light, depending on if that light is arranged the way we want it to be arranged. And of course, we could take this material and rotate it or do whatever we want, where the slits, the holes in the material, are oriented in any angle we want. So if what we want is to allow light which is polarized at 30 degrees for some reason, then we would just create this material and have the slits be at 30 degrees. Now, this is a very big simplification, okay? In actuality, this is not really what's happening. There's a lot of weird stuff behind the scenes, which requires the use of things like quantum mechanics to explain how things happen. But kind of a visual interpretation of how these filters work is like this. The light can fit through the material if the polarizations align correctly, and it's blocked by the material if the polarizations are not aligned. So the question is, what calculations can we do to kind of predict ahead of time how to set up the system if what you want to do is allow a certain amount of light through? Or another way of saying it is, if we have a system of polarizers, these filters, and we shine light through, what's going to come through and what will be blocked? This is called the law of Malice. This is the equation which allows us to do that calculation. What is it? Very easy. It says the intensity, you can think of intensity as brightness, the intensity of the light, which makes it through the polarizer, is given by, well, first of all, you need to know what was the original intensity, because if all the light comes through, then the intensity is whatever it started with. So I naught is the original or the initial intensity of the light, times the effect of the polarizer, which is cosine squared of theta. Theta, this is the most important part, theta being the difference in angle between the light coming in and the polarizer or the filter. So the important part about this is, given a problem, you don't just see, okay, what angle is the polarizer angle that. Is it at a 30-degree angle, a 60-degree angle? What's the angle of the polarizer? That's not the theta. The theta is the original light coming in is at a certain angle, let's say 90 degrees, and the polarizer is at 30 degrees. Well, theta is the difference between those. How much difference is there in this angle? I'm at 90 trying to get through something that's at 30, so I would do 90 minus 30 to get an angle of 60. That would be what I'd put for theta. And so let's try some examples. First example, let's say we have light polarized upwards. This is the symbology we will use. This up arrow represents there's light here polarized upwards, vertically polarized light. Another way of thinking about it mathematically is this light is currently at 90 degrees. And then I'm going to try to send it through this filter. And let's say this filter is at 30 degrees. And that's the symbol I will use for the filters. A square sheet with this arrow inside, and the arrow's orientation tells you the angle for the polarizer. In this case, it's angled, and I put the little angle on top just so you can see this is a 30-degree polarizer. And the question is, of course, what's the intensity of the light that would make it through this polarizer? So we use the law of Malice. We say the intensity which makes it through is the initial intensity. Well, this in these classes we do, whether it's this class or general physics, we're not going to put a number for initial intensity because it doesn't really matter. Of course, in real life, if you're actually doing real experiments, you'd know this number and you'd plug the number in. But because we're doing, the theory here, we're just learning the fundamentals, just keep this as a variable. I naught is just I naught. We don't put a number for it. So it's whatever the initial intensity is, I naught, times cosine squared theta. All right, well, initial intensity times. We have light at 90 degrees. It's a vertical polarized light. Vertical means 90 degrees. It's trying to get through a filter, which is polarized at 30 degrees. So if I'm trying to get through a filter, I need a cosine squared for the filter. And what's the angle? The angle is the difference between the light coming into the filter and the filter itself. So for this one, we have light, which is currently at 90, and it's trying to fit through something which is angled at 30. So I subtract the two, 90 minus 30 gives me an angle of 60 degrees. And so now I've made it through. The light has passed through the filter. How much light is there? 0.25 times I naught. And that's how the law of Malice works. Light is starting, trying to make it through some filters. In this case, we have one filter. We want to know how much light will pass through, so we do cosine squared of theta, where theta is the difference between the starting light, in this case, and the filter. So 90 minus 30 is 60. Cosine squared of 60 is 0.25. So the intensity of light that makes it through is 25% or 0.25 times the initial intensity. So most of the light is blocked. Only some of it makes it through. Only a quarter of the light makes it through in this case. The rest is blocked by the filter. So any questions about this so far, of course? Well, that's what we did last time. Okay, so now we're going to continue it by saying, what if these other situations happen? So for instance, one situation which can happen is, what if instead of the light starting polarized in a certain direction, we start with unpolarized light? So say the light's coming from the sun and we have this filter and we want to know how much of the light coming from the sun will make it through. Well, the symbol we use for unpolarized light, or the symbol I use, is this symbol here. Okay. This stands, it's kind of like some of the light is up, some of the light is to the right. This is randomly polarized. So this is a symbol I use for unpolarized light. And that light wants to make it through this filter. And let's say it's the same filter. Again, 30-degree filter. Now, how do we handle this situation? Well, we have law of Malice. That's all I have. So I better use it. I've got the intensity of light that makes it through is the initial intensity times cosine squared theta. Now, here's the thing. This is a rule you need to know. The rule is this. If the light is polarized in a certain direction, and that light tries to go through a filter, which is in some other direction, then you need a cosine squared theta for that filter. However, if instead the light is unpolarized and it's trying to get through a filter, you don't need a cosine squared theta anymore, because we know automatically every single time it always blocks half the light. No matter what kind of filter you have there, no matter what the angle of the filter is, it doesn't matter. If the original light is randomly polarized, it's unpolarized, then any filter you put in front of it will always block half the light and thus allow half the light through. So we immediately know the answer is just 1/2. We don't have to do any calculation for it. Anytime you have unpolarized light and you send unpolarized light through a polarizer, half the light makes it through. No need to do a cosine squared theta or anything like that for that particular filter, because we know that filter will always block half the light. And the way to think about it is, let's say the filter is vertically polarized, like this picture up here, and the original light is unpolarized, so some of it's up and some of it's horizontal. But when all that light is trying to be passed through this filter, only the vertical stuff makes it through, and the horizontal stuff is blocked. So if it's random, you would say, well, half the light is up and half the light is horizontal. So half the light would be blocked, half the light would make it through. So that's the rule for unpolarized light. Unpolarized light, making it through a filter, half the light makes it through every time. Don't worry about the cosine squared theta for that. Okay, any questions about that little rule? All right, next bit of complication. How about the fact that it's possible that maybe we want more than one filter? What if instead of just having a single filter sitting there, maybe we have 2 filters, one right after the other? What does this look like? How do we handle this situation? So say we have light polarized up. There he is. And then we're going to send that light through 2 filters. Let's say this guy at 30 degrees and this guy at 45 degrees. And now this is my system. Now what I have is light that has to make it not just through the first filter, but also through the second. And so what I expect is that the first filter is going to block some amount of light. And then whatever makes it through, that little bit of light now has to make it through this next filter. So the second filter will block even more. How do I handle it? It turns out that the rule you can think about is for every filter, you're going to multiply another cosine squared theta. Okay, so just like the first example, we had one filter sitting there, so we have one cosine squared theta to worry about. Here we have 2 filters. Each one of those things has to give us a cosine squared. And so the question would be, okay, you have two cosine squares. Do you add them? Do you subtract them? Do you multiply them? It turns out you multiply the cosine squares. So again, we use law of Malice. I is equal to I naught cosine squared theta. That's the law of Malice. For our particular example, what do we have? Well, the original light is vertical, so I know that means it's at 90 degrees. So I have the initial light is sitting there. Then it tries to go through this first filter. The first filter is going to give me a cosine squared theta. But what's theta? Well, theta, of course, is the difference between the angle coming into the filter and the filter itself. My light is initially at 90. I'm trying to get through 30. 90 minus 30 gives me an angle of 60. Now I could say, okay, whatever this is, that's the amount of light that has made it through the first filter. So now I have light past the first filter trying to get to the second. But here's the interesting thing. In order for the light to have passed, that means it had to be at the 30-degree angle. So that means I now have light sitting over here past the first filter, which is now at 30 degrees because the light made it through the filter. And since the filter was at 30 degrees, the light that makes it past the filter must be at 30 degrees. Okay, no big deal. Now we're there, and that light is trying to make it through the second filter. Well, I have another filter. That means I need another cosine squared. But what do I use for his angle? His angle is not 90 minus 45 because the light that's going to hit this second filter is not the original light anymore. Instead, the light that hits the second filter is whatever made it past the first one. And the light that made it past the first one is at 30 degrees. So the angle for this cosine squared theta is 30 degrees, which is where the light is now, minus the 45 of the filter. So 30 minus 45 is 15. And so 15 would be the angle I use for him. Now, here's a note. Technically speaking, I should say it's 30 minus 45 is negative 15. But mathematically, there's two reasons we don't worry about it being negative. We just make it positive. The first is cosine, the cosine function is what's called an even function. And all you need to know for now, you'll learn a lot more about this as you go more and more advanced physics and math. All you need to know is an even function means, for instance, cosine of theta is the same as cosine of minus theta. So cosine of 15 is the same as cosine of minus 15. It's the same number. So I could either write cosine of 15 or cosine of negative 15. It doesn't matter. They're both going to give me the same answer. And so why worry about sticking a negative in there? The second reason we don't have to worry about it is because it's cosine squared. So even if plugging in a negative angle would have given us a negative answer, we square it anyway, which would give us the positive answer. So at the end of the day, all you need to worry about is when you take the difference between the angles, whether it's positive or negative, just make it a positive number. That's why I don't say it's a cosine squared of negative 15, because it doesn't have to be. Just make it positive 15. It looks nicer. And of course, the other important thing is to note that once light makes it past the filter, we don't think about the initial light anymore. We now look at what is the light currently at, which is why the second cosine squared is not 90 minus 45, but instead is 30 minus 45. Because the light made it through the first filter, which means that light has to be at the filter's angle, which is 30. So that's why it's 30 minus 45. So any questions about this particular example? Very important because, of course, most of the problems we're going to be doing will have multiple filters, obviously. All right, let's try another example then. Let's say we have light currently polarized like this, and let's say this is 45 degrees. And that light is going to be passed through these 3 filters. Let's say I have 30 degrees, vertical, and then horizontal. So there's my new system. And same question, what intensity of light will make it through this system? All right, well, we're going to do the same thing. I mean, obviously, we only have one equation to work with. It's law of Malice. I is I naught cosine squared theta. So what do we have? Initial intensity is sitting there. We have light that's polarized in a certain direction, trying to make it through a filter. So we need a cosine squared theta for him. What is his theta? Well, our light is currently at 45 degrees, and he's trying to make it through a filter that's at 30. So 45 minus 30 is 15 degrees. Now that light has made it through this first filter. So now we have light sitting here, past the first filter. His angle must now be 30 degrees. Now that light wants to get through the second filter. Well, that means I need another cosine squared. And what's his angle going to be? Well, the light's at 30. This second filter is vertical, which means he's at 90. So 30 minus 90 is 60 degrees. All right, no big deal. I'm now past the second filter. Now the light that made it past the second filter is at 90 degrees because he made it past him. Now that light wants to make it through the last filter. So I need another cosine squared. Now, what do I use for him? Well, he's currently at 90. He's trying to get through a filter which is horizontal. That means he's at 0. So 90 minus 0 is 90. And now I'm done. I started with light, it polarized in a certain direction. I went through 3 filters, so I need 3 cosine squareds. The first one is 45 minus 30 is 15. Now my light is at 30. That 30 is trying to get through 90. 30 minus 90 is 60. Sorry. Now my light is past him and he's at 90. So 90 trying to get through this last guy is 90 minus 0 is 90. And if I plug all this in my calculator, I get 0. That means no light makes it through this system. All of the light is blocked by these filters. Okay, well, that's fine. That's the way it is. This filter setup, however it's arranged, happens to block 100% of the light. So no light makes it through. Now, here's some good news. If you practice this stuff enough, you get really comfortable with it, there's a little shortcut. And a little shortcut goes like this. If you have 2 steps one right after the other. Which are perpendicular. The answer is always 0. So what does that mean? Look at this last example we did. Here, these two steps, this one and this one. Notice these two filters, one right after the other, are perpendicular to each other. The first filter there is at 90. The second filter is horizontal at 0. Well, vertical and horizontal are perpendicular to each other. And anytime you see that with nothing in between, that is, there's not another filter between these two, it's just this filter and then the very next filter is perpendicular. That will always block all of the light. Now, it also works if the light initially, let's say we have light initially vertical and the very first filter is horizontal, and then you have other stuff, let's say, no big deal, after it. This is also 0 because initially the light is vertical and the very next step with nothing between it is horizontal, perpendicular to it. It doesn't matter what comes after, and it doesn't matter what came before. If you have two steps, one right after the other with nothing in between that are perpendicular, the answer is 0, and you don't have to do the calculation. Now, you have to be careful because if you have this, situation where if you notice this is vertical, this is horizontal, they're perpendicular to each other, but there's a filter in between. So it's not the very next step is perpendicular, but somewhere later. This is not 0. You actually have to do this calculation. This will let light through. Okay, so you have to be careful. You can't just say, oh, there's two steps in this problem that are perpendicular. I know the answer is 0. No, it's only 0 if the perpendicular steps are one right after the other. Like this, one right after the other with nothing in between. Or here, one right after the other with nothing in between. For those cases, yes, it's 0. You don't have to do the calculation. You can just look at it and see. Now, if you're not confident, if you're afraid, oh, there may be a chance where I mess up and I think it's 0, but maybe I just forgot something. I'm not really sure. Then don't worry about the shortcut. Just do the law of malice like I did here. I actually did the calculation and it gave me 0. This is the nice thing. The actual calculation will give you the right answer every time. This shortcut, this trick, is there for if you know when to use it, if you're comfortable enough to use it, then you could save a little time when you don't have to do the work. If you happen to have an example where the trick will work, well, why go through the 2 or 3 minutes of doing the calculation when you know the answer has to be 0 at the beginning? So it's up to you if you want to use the trick or not. Of course, if you use the trick when you're not supposed to, the answer is wrong. So you have to be careful. But if you don't want to use the trick, then do the normal law of malice calculation like every other example we've been doing thus far, and you'll be fine. You'll get the answer, no big deal. All right, so any questions about this? Well, that's really all I have. This is all there is to polarization. All that would be left is to just continue to do a bunch of examples, but they're all just like this. No new things, no tricks, no things I didn't show you. You're either going to start with light that's polarized a certain way, or you start with light that's unpolarized. You have a certain number of filters that you're trying to make it through, and you want to know how much light makes it through. Normally, every filter you have, there's a cosine squared theta for him. The only time that's not true is when you have unpolarized light. If you have unpolarized light, the first filter is only a half. Now, I better do an example just to be clear. What if we have more than one filter? So this will be our last example. What if I have this example here? Unpolarized light is trying to make it through a series of filters, 45 degrees here, and let's say 60 degrees here. Okay, so there's our question. What's the intensity of light that makes it through this system? All right, so usually I would say I have two filters, so I need two cosine squared thetas. However, the light initially is unpolarized light. So what that means is this first filter, I don't do a cosine squared theta. Instead, I just write a half. That's it. First filter done, 1/2. Now I'm past the first filter. And since I'm past the first filter, I know my light must now be at whatever his filter angle was, which is 45 degrees. So now that light is trying to make it through the second filter. Well, now I'm not unpolarized. I'm now polarized at 45 degrees. Since I'm not unpolarized anymore, now I need a cosine squared theta for the next filter. So cosine squared, what's his angle? Well, he's at 45. He's trying to make it through 60. So it's 15. And then I'd stick this in my calculator, get a decimal answer for this, as usual. So note, even though I have two filters, since the light initially was unpolarized, the first filter does not get a cosine squared. Instead, that cosine squared is just 1/2. But every filter after that, we do need a cosine squared theta because now he is polarized. Okay, so just be careful about that. The first example I did only had one filter, so it may have been enticing to say if you ever have unpolarized light, the answer is always a half. That's not true. What's true is the first filter gives you a half, but you may have more than one filter. And if you have more than one filter, the first one gives you a half. Every other one, you have to do the cosine squared theta, just like always. Because once you've made it past that first filter, you're no longer unpolarized. You're now polarized at a certain angle. And the rule is you need a cosine squared theta for that. So that's it. That's all of our material. We're now done. We've done polarization. Of course, there is another few topics in optics we would normally do in general physics, but we're just running out of time. We had several breaks in the semester. We couldn't get to it all. And instead of trying to rush through it, I'd rather just make sure we understand what we can do. And when we get to that material in the next class, then it'll just be new. So this is polarization. Of course, practice problems and all of that are posted on Canvas, so certainly be looking at that. I will be posting a homework assignment for it to make sure you get some official practice for it. Tuesday will be our official last day of class, and what we'll do is just a final exam review. So I'll go back over all the topics we've discussed throughout the year or the semester and let you know what to expect from the final exam. It is cumulative. And if you want a little head start to know what to study, if you want to start studying early for your final exam, then I would start looking at your old tests, because if I felt the topics important enough to put on the tests, then likely that's what I find important for the final exam as well. So look at the old tests, work those out, see if you can handle those problems. If you could, you're going to be fairly good for this final exam. Of course, the only thing new on the final exam will be this optics stuff we've been doing since the last test. Okay, we just didn't have enough time to have an official test on this, so it'll be tested on the final. But if you start studying the old tests, study the stuff we've been doing here, you'll be perfectly fine for the final exam. But of course, I'll get into more detail on Tuesday about that. So unless you have any questions for me, you are free to go. And I will see you on Tuesday.